we continue our discussion of section 5.3. In section 5.3, we want to find the solution of this boundary value problem. In short, in order to find the solution, first, we skip the middle condition. We consider this new boundary value problem. It's the equation, which is over here, and this, which is over here. Then, last time I showed you how to find infinitely many solutions of this. These infinitely many solutions are written over here. So, here we have infinitely many functions because n is any positive integer. Next step, in appendix 2, we show that if u1, u2, and so on are solutions of boundary value problem 2, then any their linear combination is also a solution of this problem. Here is why. U1 is a solution of this problem, means a row number 1. U1 is a solution of the equation, and U1 satisfies this condition. U2 is a solution of this problem, means a row 2, and so on. Un is a solution of our problem, means a row n. Next step, let us multiply each row by C1, C2, and so on, Cn. After that, let us add these equations together, done, and these conditions together, done. Observe that since U is a linear combination of U1, U2, and so on, Un, the left-hand side of this equation, which is over here, is simply du dt. For the same reason, the expression after alpha square here, this expression, is the second partial derivative of u by x. Similarly, what is written here, according to this, is simply u of 0t. What is written here, thanks to same expression, is u of lt. In total, a left-hand side, which is this, is equal to a right-hand side, which is this, and this, which is u of 0t, is equal to this, which is u of lt, is equal to 0. What is written here means not only u1, u2, and so on, un, but also this u is a solution of our boundary value problem. Why care about this? Well, here's why. Once again, any such u is a solution of this. However, remember, originally, we care about boundary value problem 1, and we cannot really expect that for a given f of x, our u's will be equal to f of x. However, since any their linear combination is a solution of this problem, now we have some hope that if, say, f of x is of a special form, then it will be possible to find C1, C2, and so on, Cn, such that this, when t is 0, is equal to our given function f of x. By the way, it's exactly what happens in this example. F of x is of a very special form. Therefore, if you set in this formula C1 is 0, C2 is 0, C3 is 2, and then C4, C5, C6, C7 are 0, but Cx is 5. And if all other C's are equal to 0, then this is equal to this. So, if our function f is of a very special form, it is possible to find C's such that this is equal to this. And therefore, the solution of the boundary value problem will be what is written here. We discussed it last time. However, now imagine that f of x is equal to, say, 1. If f of x is equal to 1, one can show that it is impossible to find numbers C1, C2, and so on, Cn, such that the whole expression is identically equal to 1. Therefore, big question is, what do we do in this or other situations? Here is the answer. It turns out that over here, we can replace capital N by infinity, which means instead of a finite sum, let us consider an infinite series. It's exactly what we have on the bottom on page 1. Question: can an arbitrary function f of x be written as an infinite, a linear combination of these functions? Can we find C1, C2, and so on, such that f of x is equal to this? Remarkably, the answer to this question is yes. We will discuss it in section 5.5, but in order to understand the ideas that we describe in section 5.5, let us first go to section 5.4, which is called Fourier series. Let's take a look at this theorem. Suppose f and f prime, prime means derivative, are piecewise continuous functions on this interval. Step 1. Find a nth and b nth using these formulas. Step 2. Write down this infinite series. Question: what is the relationship between this series and f of x? Here is the answer. This series converges to f of x. Converges in simple words means is equal to f of x. This infinite series converges to f of x if, number 1, x is not one of the endpoints. Remember, originally x is greater or equal to negative L and lesser or equal to L. Here, case 1, suppose x is strictly greater than negative L and strictly lesser than L. Suppose x is not one of the endpoints, and also suppose that f is continuous at x. then this series converges to f of x. Case 2. Suppose x is still not one of the endpoints, but f is discontinuous at x. Then our series converges to this, where f of x plus 0 denotes the limit from the right of f at x. Similarly, f of x minus 0 denotes the limit from the left. Lastly, case 3. Suppose x is one of the endpoints. Then our series converges to this, where f of L is again a limit from the left, f of negative L is a limit from the right. Folks, think about questions here.
What is f in this case?
F in this case is a given piecewise continuous on the integral function.
Okay, got it. Thank you.
By the way, let me make the following remark. This theorem does not allow us to solve this problem yet, because in this particular case, we want to write f as an infinite linear combination of signs only. Over here, we have both sines and cosines. But as I said, we will fix this problem in section 5.5. Here is another difference. In this section, function is defined on the integral from negative L to L. Over here, from 0 to L. But once again, this will be fixed later. Any other questions?
Why does Bn not start at 0?
Yeah, very good question. Observe, and this is not a misprint. Here, for An, n starts from 0. For Bn, n starts from 1. Here is why. If n is equal to 0, B0 is simply 0. Was that your question?
Yes.
Other questions?
Why do the formulas have cosine n pi x over L and sine pi n pi x over L?
Unfortunately, we do not have time to explain what is behind these formulas. But in short, in order to come up with these formulas, step 1, write the following expression. F of x is equal to this. Step 2, multiply both sides of this expression by cosine of n pi x over L, and then integrate both parts. You will see that almost all terms are equal to 0. If we simplify the remaining expression, we will get this. Did I answer your question?
Yeah, thank you.
Okay, now examples. Example number 1. F of x is given. It's a piecewise function. We want to find its Fourier series. Step 1, find A0. For convenience, we copy this formula over here. Then we replace L by 1 because according to what is written here, L is equal to 1. We replace L by 1 here, 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 and here. Done. We also replace n by 0. Done. 1 over 1 is 1. Cosine of 0 is 1, disappears. So a0 is equal to integral from -1 to 1 f of x dx. Next, by calculus 1, integral from -1 to 1 can be split into two integrals, from -1 to 0, and then from 0 to 1. You may ask me a question, can we use another number instead of 0? In general, the answer is yes. We can put any number between -1 and 1 instead of 0. For example, we can put here 1/2 and here 1/2, or here -1/3, here -1/3. But for our purposes, we put here 0 because over here 0 and over here 0. Once again, if instead of 0 here we have, say, 1/2, or we put here 1/2 and here 1/2, here is why. Observe that over this integral, which is over here, f of x is equal to 0. It's exactly what we put here. And over this integral, which is over here, f of x is equal to 1. And we put here 1. Lastly, integral of 0 is 0, disappears. Antiderivative of 1 is x. We plug in 1, we plug in 0. A0 is equal to 1. Guys, any questions about A0?
Thought you couldn't take an integral if it's a discontinuous function.
No, we can. We absolutely can. Please take a look at this. We click on calculus, and then we click on the definite integral. It's over here. If f is continuous on AB, or f has only a finite number of jump discontinuities, integral exists. It's exactly what we have here. F has finite number of discontinuities. At 0, our function is discontinuous. Do not confuse integration and differentiation. We cannot take the derivative if our function is discontinuous, but we can perfectly integrate this function. Does this answer your question?
Yes, thank you.
Next, let us find a n where n is greater or equal to 1. Again, for convenience, we copy this formula. And then, as before, we replace L here, 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 and here by 1. 1 over 1 is 1, disappears. And pi x over 1 is n pi x. Then we split this integral into two pieces. Over this integral, f of x is 0, according to what is written here. Over this integral, f of x is 1, according to what is written here. Integral of 0 is 0, disappears. 1 times cosine is cosine. Next, by calculus 1, use substitution, antiderivative of cosine n pi x is 1 over n pi sine n pi x. We plug in 1, done. We plug in 0, done. Observe that sine of 0 is 0. But what is sine of n pi? Please take a look at the graph of sine. Note that sine is equal to 0 at any integer multiple of pi. It's exactly what we have here, sine of n pi 0. 0 minus 0 is 0. Conclusion, an is equal to 0 for any n greater or equal to 1. Now, once again, a0 is 1. All other a's are equal to 0. Similarly, here is the formula for Bn. We copy it from the theorem. In this formula, as before, we replace all else by 1. We simplify. We split this integral into two pieces. We replace f of x by 0 here. We replace f of x by 1 here. This integral is equal to 0. 1 times sine is sine. By u substitution, antiderivative of sine n pi x is over here. We plug in 1 instead of x, done. We plug in 0 instead of x, done. Observe that cosine of 0 is 1. Now let us talk about cosine of n pi. Let us look at the graph again. Looking at the graph of cosine, we conclude that cosine of even number times pi is 1. Cosine of odd number times pi is negative 1. Once again, just take a look. Cosine of 0 is 1. Cosine of 2 pi is 1. Cosine of 4 pi is 1. But cosine of 3 pi is negative 1. Cosine of pi is negative 1. It's exactly how we come up with this result. If n is even, cosine of n pi is 1, and 1 minus 1 is 0. If n is odd, cosine of n pi is negative 1. Negative 1 minus 1 is negative 2. Negative 2 times negative 1 is positive 2. And now let us write down the series. Please take a look at this. Over here, what is written here is same formula. We just write down more terms. Here we have 1, 2, 3, 4, 5 terms. Here we have more terms, but essentially it's same formula. Next step, or replace a0 by 1 because we know that a0 is 1. We replace all 0 terms by zeros. 0 terms are all other a's, zeros, zeros, and even b's, again zeros. We get rid of 0 terms. We get rid of this, this, and this. Done. Lastly, we replace all odd b's by this formula. Done, 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 and so on. Finally, in order to come up with a sigma notation, factor out the common term, which is 2 over pi. It's over here. And observe that on the tops and on the bottoms, we have only odd numbers, which means 2n minus 1 here and 2n minus 1 here. Part 1 is done. What we see in front of us here is the Fourier series of our given function. Part 2, we have to determine at which points our series converges to f of x, at which points our series converges to this and to this. So here's how we do it. Note that our function is continuous everywhere except for 0. Therefore, our series converges to 0 here and 1 here. Because f of x is equal to 0, so we put here 0. And f of x is equal to 1. We put here 1. Once again, by the theorem above, our series converges to f of x. If x is not one of the endpoints and f is continuous at x, but f of x is equal to 0 here and 1 here. So our series converges to 0 for any x between -1 and 0, and our series converges to 1 for any x between 0 and 1. Despite the fact that the formula is pretty complicated, it turns out that no matter which number we will plug in between -1 and 0, the whole thing is equal to 0. And no matter which number we plug in between 0 and 1, the whole thing is equal to 1. Next, suppose x is not one of the endpoints and f is discontinuous at x. This point is 0. Observe that our function is discontinuous at 0. According to the theorem, our series converges to this. However, before we discuss the remaining two cases, let us find the value of our series at the point of discontinuity and at both endpoints using straightforward approach. Let us just plug in 0 and ±1 into our series. We get this, this, and this. Note that in all three cases, all signs are equal to 0. So the result is 1/2 in all three cases. Conclusion: if x is between -1 and 0, our series converges to 0. If x is between 0 and 1, our series converges to 1. However, if x is either 0 or ±1, our series converges to 1/2. Of course, we can come up with these results applying the theorem. According to the theorem, if x is not one of the endpoints, and if x is a point of discontinuity, our series converges to this, where f of x plus 0 is a limit from the right. Please take a look at this function. If we are on the right, f of x is equal to 1. This is why we have 1 here. Similarly, if we are on the left, our function is 0. And here we put 0, in total 1/2. Lastly, talking about the endpoints, we apply this formula, where both are limits again. Now, f of 1, looking at our function f of 1 is 1. It's exactly what we have here. And f of -1 is 0. It's exactly what we have here. Again, we have 1/2. Guys, any questions here?
I don't really understand how it converges to 1/2 if we established earlier that the value is either 1 or 0 or -1. I forgot what the values were. I think it was 1, yeah, 1 and 0.
Very good question. Observe that over here, x is strictly in between. Here, x is strictly in between. these three cases, x is equal to 0, x is equal to 1, x is equal to -1. It's not this case, and it's not this case. Make sense?
Yeah, I got it.
Other questions?
I'm still confused about what the Fourier series tells us about f. Like, what is their relationship to each other?
Once again, in simple words, this is equal to f of x if x is not one of the endpoints and f is continuous at x.
Okay, that makes sense. And then at the endpoints and the discontinuities, those numbers we got, those 1/2s, what do those mean?
Well, once again,
For f.
this means the following. If we have an endpoint or a point of discontinuities, we have something else.
But it doesn't relate to f.
It relates somehow. It's either this or this.
Okay.
Other questions?
Does this work for any function f?
It's written. F and f prime are piecewise continuous on this interval.
Okay.
Let us discuss this example. This example is similar to the previous one, it's just a little bit more technically complicated. So here's the function. We want to find its Fourier series. Step 1, as before, find A0. So we apply this formula for n is equal to 0. Know that cosine disappears. It's exactly what we have here. There is no cosine. And observe that since x is between -2 and 2, L is 2. Then we split this integral into two pieces from -2 to 0, because here we have 0, and then from 0 to 2. Our function is equal to 1 over this interval. Here's 1. And our function is equal to x over this interval. Here's x. By calculus 1, antiderivative of 1 is x. Antiderivative of x is x squared over 2. We plug in the numbers. We do arithmetic, 2. So A0 is equal to 2. Now, in order to find an and bn, where n is greater or equal to 1, we apply these formulas, which are again taken from here. Next, as before, we split this integral into two pieces, this integral into two pieces, and then in order to find antiderivative of cosine and antiderivative of sine, it's written in appendix 2. We use u substitution. However, in order to find these two integrals, we apply integration by parts. Work is here and work is here. And now again, looking at the graphs, we conclude that if n is even, cosine is 1, therefore the whole thing is 0. To the contrast, if n is odd, cosine is -1, -1 minus 1 is -2 times 2, -4. Similarly, if n is odd, all bn's are 0. If n is even, bn is -2 over n pi. We are done with a's and b's. Then, as before, we write down many terms of our general series. We replace A0 by 2. We replace odd b's by zeros, even a's by zeros, and get rid of the zero terms. Done. Lastly, we use these two formulas to replace the remaining a's and b's. Here is the final answer. In order to simplify, let us first group all cosine terms together. Done. And all sine terms together. Done. After that, observe that over here, the common term is 4 over pi squared. Factor it out. The common term here is 1 over pi. Factor it out. And lastly, note that over here, we have all positive integers inside sine and in the denominators. So if we use sigma notation, top is sine of n pi x over n. Over here, 9, 25, and so on. These are squares of odd numbers. It's exactly what we put here. 2n minus 1, 2n minus 1 squared. This is our Fourier series. Lastly, according to our theorem, our series converges to f of x. And remember what is f of x? 1x. Therefore, at any point x, which is not one of the endpoints and which is not the point of discontinuity, our series converges to 1 here and to x here. Case 2. Suppose x is the point of discontinuity, means 0. According to the theorem, our series converges to this, where here we have limit from the right and here we have limit from the left. Let us look at our function. On the left, it's 1. It's exactly what we have here, 1. On the right, it's x, but x is equal to 0, so it's 0. It's exactly what we have here, 0. So 1/2. Lastly, let us examine the endpoints. F of 2 is limit from the left, f of -2 is limit from the right. Let us take a look. From the left, it's x, so we put here 2. On the right, it's 1. We put here 1, 3/2. Guys, now we are done. Any questions here?
Does the 3/2 mean at both endpoints?
Exactly. So another thing about this theorem is no matter which point we plug in, at both endpoints, our series converges to the same number because the expression is same. No matter we have plus L or minus L.
Okay, thank you.
Other questions?
Why does the Fourier series require a piecewise function?
You asked a very good question. Probably your question is, what is piecewise? Piecewise means the graph of our function is a collection of pieces. For example, the graph of our function can be just one piece without discontinuities. You see what I mean?
Oh, okay, that makes sense.